one of the textbook questions. If a resistor of R ohms is connected across the battery of E volts with internal resistance R ohms, then the power involved in the external resistance is given by this function. Okay, so if you are, take any physics class, you can even derive this formula if you want. Okay, so I'll give you how this formula really coming from, but for math class you don't need that. Okay, so if you think it's like total resistance, R total, this is just I explained how the formula really comes. Okay, so total resistance is internal resistance plus resistance R is connected across the battery, and internal resistance plus capital R. It's like R plus R. Okay, and if you want to say the current I in the circuit is given by Ohm's law. You know Ohm's law, right? Ohm's law, according to the Ohm's law, I equal the voltage. Voltage is E. Anybody remember from the physics class? It's like E over resistance, which is the current. It is the total. And if you need the power has the formula P is equal to E to the power 2 I. Okay? Oh, sorry, I to the power 2 E. The power is, you can say the power is dissipated. Okay, dissipated in the external resistance R. System. So now these are basic equation. I just want to tell you how this formula really coming. So you can replace this I with that, and you can get that formula. Okay. For example, if you plug, because your I is equal to E over R plus simple R and you have E. I square R. This should be I square R. Okay. So let's convert this. E square R plus R square. This is the power. Okay. Clear? So I just explain how the formula really derived. First you get the total resistance, use the Ohm law, plug that I back to here. Okay. So three formulas like total resistance, it's not a formula, you just add the resistance. And this is Ohm law, this is how the power connect with current and resistance. Okay? Right. What the question asks in the calculus, you can use the calculus to find out maximum power. You can change the R here. Okay? And I'm asking what should be my capital R to get the maximum power. Okay, so it's like you can treat the power as a function of capital R. So I can write this one as power as a function of R, because they say E and simple R you can treat as a constant. E and R are fixed, but R varies. Okay, good everybody. Now you need to do is take the derivative of power with respect to R. So if you want to write it like this as a dash, or the P prime or dP over dR. This is what you are really doing. Take the rate of change of power with respect to resistance. Okay. Now you know this how to differentiate. Take it as a quotient rule and do the derivative. Because you have R here and here. This is a constant. You can think it's like a. This is like 100. This is like 5, like numbers. It's not really matter when you take the derivative. Can do it. Okay. Use the quotient rule. Take the denominator and get the derivative of the top. What is the derivative of the numerator? Yeah, thanks. Power 2. Denominator is power 2, yes. The derivative of the numerator? E to the power 2, because it's just, you can think it's like x. Just x. Because I'm taking the derivative with respect to r. Okay? It's e to the power 2. Minus e to the power 2 times r, because this is your numerator, and take the derivative of the denominator. Good. So we have a textbook question, so we are trying, okay? So power connected with the voltage, resistance, given by this relation for the formula. So I want to find what is the maximum power. How do I choose my capital R? What my R should be to get the maximum power. Okay? So you can change it. Okay? That's what you are changing. Okay? Right. So what is the derivative of this? 2 R plus R power 1, and you take the derivative of the inside, but it's just 1. That's it. You done with the power rule and you go to the inside function, it's just R you have. This is a constant. It's gone. This is just 1. You will multiply by 1, doesn't change anything. Okay? And you have R plus R power 4. Now, you know, maximum minimum point, doesn't matter how the relation connected, always you can find by setting the derivative equal to 0. Because extrema you can get by set up your derivative equal to 0. So you set the derivative equal to 0. And you get that relation. So remember, this is never 0. I mean, this is like some number to the power 4. In application, it's like a number, right? So it's never 0. The only way you can take the derivative 0 by thinking about the numerator. So you always set up numerator equal to 0. Okay, take your time and set up the numerator equal to 0 and get the connection of, get your R, capital R, in terms of other variables. Okay, that's what you want to do. So this gives me R plus R square, E square. I have minus E square R. 2 I can take out. R plus R. I'm going to set this equal to 0. Setting my derivative equal to 0 is same as, you can think it's, you make this equal to this if you want. Or you can think the entire numerator you set it equal to 0. Good? Let me check if anything, yeah, 2 I can get, yeah, all good. You can bring it to other side and put the equal sign here. So let me write it one more time, okay? So, oh, maybe before that, let me see. Yeah, I want to solve this one because I have my capital R everywhere. I can't quickly subject it. So my goal is to get capital R, okay? This is my goal. Because I need to know for what capital R my P become maximum, okay? So I need my R. So I'm gonna do, this is like a binomial formula. You can use R square, 2R, R square. Do you remember that from pre-calculus? We did A plus B square. That's why you learn those things, because this kind of application formula you see in your engineer class, always you have certain things plus square, cube. That's why you need those expansion. Otherwise you don't, you cannot do any calculus without, the algebra. So you have E square, and I can bracket, unfold the bracket. So it's like 2E square R square minus 2E R square R. Now I can see some terms, let me see if I can. Yeah, some terms cancel out. R square, E square, let's see. R square, E square. 2R, E square. R square, E square. And I have 2E to the power 2, R to the power 2. Okay? 2E, R. This is common. Also, can you see, guys, this one cancel out? You see those terms cancel out. Some similar terms available, those are cancelled out. These two cancel out, and it gives me e to the power 2, r to the power 2. This one remains r to the power 2, e to the power 2, and 2 times r, e to the power 2 cancel out. Please do it yourself and really make sure you get that correction, okay? So understand all the steps, not just, write what I'm writing on the board. Okay, so you have to make sure you do algebra your own and see those cancellations. Good? What do you think? What is your capital R? E really cancel out. Can you see that? This e to the power 2, you can take out. Can I write like this? Yes, I can take, this is really I can take a minus e to the power 2. I take minus e to the power 2. What do you think? Is voltage. Voltage is not 0. It's a positive number. Okay? This is like a number and you have a minus. It's like minus, minus 100, minus 50 or something like that. This is not a 0. This number is not a 0. Whatever it is. So only way this equation can be 0 by setting this one equal to 0. Clear? There's no other way it can be 0. Yeah.
Why did the r squared and r squared become subtraction when it was positive?
Because e to the power 2 is common for both.
Okay.
I take out e to the power 2. When I take out minus because I need my r to the capital R in the first place. Okay? Because it's really, I have minus there. Clear?
Clear.
And minus become plus, so it's aligned with the algebra. Okay? And this is the logic. This part never 0. You can divide by that number if you want, both sides. This is cancel out. And the only way it can zero is r to the power 2 become capital R to the power 2 becomes simple R to the power 2. So that means R is equal to R. You can't have minus resistance. If you think like a positive, this is the only situation. So that means if your capital R becomes simple R, this power function has an extrema. I don't know whether it's a minimum or maximum. You have to think about it. Okay. So this is what I'm going to do to think what happened around capital R. Okay. So this is what I'm going to do now. So if you want, you can take second derivative, which is too long. Okay. Because this kind of practical question, you have so many like letters like E, R, you know. Taking second derivative could be really challenging. So instead, you can do this. Okay, before I start, is that clear how I get this connection? Because this is the only variable. The calculus says it should be my simple R to get the extreme. Okay, so this, you can think it's like this way. So you can think, okay, this is your power function. Okay, this is how the resistance change. And when R equal R, I have a extreme point. It could be minimum like this or maximum like this. I expect to have a maximum, because that's the question asked. Okay. So now what you want to do? Tell me something less than R. Because I know when I draw the function at this point, I have a turning point at R. Simple. So this is like a zero. And I'm going to take R over 2, which is less than R. Agree? So it's like if you have 5, if you have 6, you can take 3 as a smaller number. So I don't know what is this R. That's why I choose as a half of that. Is that clear why I choose R over 2? So then I'm going to plug that R over 2 to my capital R. Is that clear? Because then I can see what happened to the derivative just below my R. And then next what I'm going to do, I will write down something above simple R, like 2R, and I plug to my capital R. Okay? Because I can change my R. And I'm really worried, I'm really drawing the graph of P with respect to my R. Because my function is, power is a function of capital R. And I'm really drawing a graph, and at this point it has a maximum. But I don't need to draw entire graph. I just want to verify it's a maximum. Okay. Any questions so far? Any question? So all what I'm going to do now is plug R over 2. Okay. Let me see. I simplified here. So I simplified all those things. So this is my numerator. I didn't do anything. So I can this is my numerator. This is my numerator. So I simplify my numerator and I come to this level. This is still my numerator. So I can replace my numerator with this one. The reason I am doing is we can do the argument easily if I simplify the numerator. Okay? So I'm going to erase this part because this is exactly my numerator. Okay? So I'm going to erase this, and my numerator, I'm going to use this guy. Okay? Maybe.
This is for your second.
Sorry?
That's for your second one. Here, because you're finding second derivative.
No, I'm not finding second derivative. I'm still in this first derivative. Okay? So, but what I'm doing is I had a numerator which I simplified over there. I'm going to write that one. Okay? So this is what I'm going to do. I have e to the power minus 2 r to the power 2 minus simple r to the power 2. Everybody agrees I can write down that one because it's the same numerator that I simplified over there. Okay? I simplified the numerator, so I'm going to use that numerator then I can make the argument nicely. Okay, so what happens if you plug R over 2 here? If you plug R over 2, which is smaller than this, it gives me negative number. You good? Is that clear? If you plug R, what happens? If you plug simple R, it's 0. That's what I need to know. That is the extreme point. But if you plug something less, you can see if you plug something less than this, it's negative. Negative times negative, positive. So that means derivative positive here. Clear? Derivative positive. Is it clear? Derivative positive, how I get derivative positive? What if I plug 2R? If I plug 2R for my capital R, I get of course positive number inside, but I have minus there, so it gives me negative. Okay? So it's like increase, because derivative positive means increasing, and this is a turning point happen at simple R and decreasing. Clear? That's how you really know it's a maximum. Is it clear? So I got my capital R equal to simple R, and I am discussing my derivative around simple R. Okay? Around the neighborhood. Okay? So around the neighborhood is, you can choose your simple R to be R over 2, and you plug R over 2. It's like you plug R over 2 like this. I'm sorry, here. For the capital R, okay? You are plugging R over 2 like this. If I plug R over 2, this is like a negative number. Okay? It's like you have 10 here and you plug 5 here. If you take the square, it doesn't matter. It's still, this is bigger. What happens if you plug 2R? Of course, this is positive. Since you have minus, you have minus. Okay? So that's how you don't take the second derivative and discuss the maximum. Otherwise, you have to take the second derivative and plug capital R equal to simple R, and you will get, because second derivative negative means you have a maximum. You can use the second derivative theorem or test to do that, but it's too long to do that because it has so many unknowns like terms available. Is that clear? The power become maximum when capital R equal to simple R, and most of the time you need to find the maximum power. So if you need to find the maximum power, you can say power maximum happen when R equal, and it will be e to the power 2R. This is 2R, so it's like 4R2. And this is R again because I have to replace this R, capital R also by R. So this is the maximum power. That's the maximum power. Is there any questions? I take the derivative, I set the numerator equal to 0 to find where the extrema occurs, and I discuss what happens around that extrema, and I figure out it's a maximum. Because less than simple R, my derivative is positive, which means my original function is increasing. Okay. Derivative positive means I'm talking about the derivative and discuss my original function. So derivative really tells you what happens to your original function. Okay. As a sometimes if you take any physics class, you have to draw this graph. Okay? Of course you can do that. Okay? So as a homework you can try to draw it. And you can plug numbers if you want for E and simple R, and see how the function really look like. Okay.